This is a summary of two of our prior works that was published this year and in the end of last year. This talk is titled Heterogeneous Data-Centric Architectures for Modern Data-Intensive Applications, a case study for in machine learning and databases. Again, the outline for this talk. First, I'm going to motivate a little bit why we need to do hardware software co-design for processing memory. Then I'm going to talk about the works that we employ such approach, which are called Mensa and Polynesia. So we start with the introduction. I guess I don't need to spend too much time here. Data movement is a problem. It happens for different reasons. Not enough locality, not enough memory bandwidth, or high average memory access time. Compute-centric solutions are failing to solve those problems, and in the end, as a solution, you have processing memory that can have the high DRAM bandwidth or shorter memory access time. So when should we employ processing memory, right? For which application? So many prior works have shown how to employ processing memory for graph processing, mobile workloads, neural networks, DNA sequence, databases, time series analysis, and many, many others. However, there is a common limitation of prior work or a pitfall that prior work can leads to or can give the impression to. So processing memory is not a one-size-fits-all solution, and processing memory architecture has a lot of limitations in terms of what can be designed. So for example, if you take into account 3D based processing memory designs, you have limit area, you have thermal problems, you have limit power budget, lower clock frequencies. If you go for 2D DRAMs, integrating computation and logic in a single DRAM manufacturing process is really challenging. So all of these need to take into account when you design a processing memory system, so you can fully leverage the potential of the overall architecture, right? So to avoid subpar performance for a processing memory solution, we need to efficiently co-design hardware and software in order to avoid processing memory constraints. So here I have an example from one of our prior works that shows for many there are 3 workloads in the x-axis and different kernels for those workloads. And then we evaluate 3 different configurations: a CPU only, a pin core where we don't do hardware software co-design, and a pin accelerator. And then you can see in the plot, by doing hardware software co-design, we can further gain performance on top of the processing memory core design, the naive implementation, let's say, or the baseline, and further improve the performance in terms of baseline. And this is in terms of performance, but in terms of energy is even further exacerbate of a problem. And how you do hardware software co-design for processing memory is not much different than what you do for a general accelerator. And in general, we follow a 2-step approach in our work to do a hardware software co-design for PIN. So let's say that you want to study a target application that you think that you can accelerate for processing memory. So the first thing that you do is to heavily profile and understand the characteristics of those that application into interest, to understand the hardware software requirements of that application, the performance bottlenecks that application is causing in its baseline system that is going to execute, and the sources of energy bottlenecks. And based on that knowledge that we gain in the first step, the insights in the first step, we then go and design algorithms and hardware taking processing memory into considerations. And in the end, you have a high performance and high energy efficient processing memory architecture. So I'm going to illustrate how this is done with 2 application domains. So the first one is machine learning for edge devices, and the second one is hybrid transaction analytical database system for cloud processing. So starting with Mensa, which is an accelerator for Google neural network in the edge device. So really briefly, why should we do machine learning workloads on the edge devices? For varying reasons, because in terms of privacy, the phone is in your pocket, it's out in the cloud. Connectivity, if you don't have internet, you can still do inference. In terms of latency, you don't have the latency of going to the cloud anymore, right? The latency is much shorter, and also the bandwidth is much higher. However, edge devices are quite limited in terms of power and computing resources. So based on that, many prior works or many companies have started developing their edge accelerators to do ML. For example, Apple has their A12 chip, and Google has the Google Edge CPU. At the same time, there in terms of machine learning workloads or particular neural networks, we have a lot of different models. We don't have only convolutions in neural networks anymore. We have LSTMs, or we have RCNNs, or we have transducers. And this creates a problem because now we have a single accelerator that is being catered for different machine learning models. So we take that edge TPU accelerator at Google, and we machine learning models also running at Google, 24 of them, and we extensively profile them to understand how the Google edge TPU accelerator were executing over there. And so briefly, what is a Google edge TPU? Is a systolic array which has DRAM and array of MAC units and on-chip buffers. How it works? So we have the ML model stored in the DRAM, and it's then the input activations and parameters are brought to the processing element array. In our case, the element array of the Google edge TPU that we consider was a 64 by 64 array, and the on-chip buffer was our 4 megabyte on-chip buffer. And we have a data flow also that maps the computation into the, and orchestrate the computation into the processing element array. So as I said, we analyzed 24 different machine learning workloads for Google and neural network models, 6 RNN transducers, 13 convolution neural networks, 2 LSTMs, and 3 RCNNs. And after we analyzed the performance and the energy of those 24 models running on the edge TPU, we conclude that the edge TPU suffer from three main challenges. The first one is that it operates significantly below its peak throughput. The second one is that it operates significantly below its peak energy efficiency. And then it was handling memory quite poorly, even though it has a specialized data flow. So the question is where these problems are coming from, right? So then we went and started doing an analysis of the software, the layers that were, or the machine learning models that were being executed on the edge TPU. And then we observed some problems. The first one is that there is a diversity in features across the different machine learning models, right? There is a variation across a model and across layers. So here, for example, I have different neural networks as dots. Each dot is a different layer, and I have two metrics: parameter footprint in the x-axis and reuse in flops per byte in the y-axis. And you can see that this varies quite broadly for different neural network models, right? So we have layers like CNNs and RCNNs that have high reuse, and layers like LSTMs that do not have high reuse but has a high parameter footprint. Likewise, when you look inside a single layer itself, we see a large variation in behavior for a single model, but different layers of the same model. For example, here I have a CNN, and then in the x-axis I have the different layers, and the y-axis I have the number of multiply accumulate operations executed by that particular layer. And then you can see for this example a variation of up to 200 times across different layers. And if you consider another model, again, you see this large, and you pick another metric, we see a variation also in that metric. Like here, the flops per byte or reuse is varying for more than 244 times. So the overall conclusion is that the main problem of that the edge TPU was suffering from that particular model is that there is a heterogeneity that the accelerator was not catered for. So we have a monolithic accelerator that was designed for probably for a particular type of neural networks, but now we have many different types of neural networks that you want to execute in that same accelerator, and that is causing the performance drawbacks and energy drawbacks for the particular accelerator. So how can you solve this this problem, right? For this edge TPU design? Then you propose this Mensa framework. So the goal of this Mensa framework is to design an efficient accelerator that can cater for different machine learning models, right? So the main idea here is that instead of designing a single big monolithic accelerator, we are going to have a framework that is going to have a combination of smaller accelerators and a scheduler that can map different layers for the most appropriate accelerator during the execution of the application. So just to pictorially show it, here we have the edge TPU, we have different models executing a monolithic accelerator. In Mensa, we're going to have different models and a runtime scheduler, which is going to decide which model should and which layer should execute in which accelerator. The runtime scheduler is a software runtime scheduler that is taking the characteristics of the accelerator and the characteristics of the layers, which both of them can be known before the execution of the application during compilation time. Those workflows are quite regular, and then do the mapping between the layer and the accelerator itself, doing the execution of the application, considering utilization, for example, or communication, and all of that in our paper. I refer to that. I don't have a lot of time to go through it. And then in the end, you have the layer mapping. The question right now is, how many accelerators do we need? And then the Mensa framework tries to answer this question, right? So we identified that even though we have 24 models and many different layers within those models, the properties of those, the properties that matter for the accelerator design tends to group into different layer families. So when you do this analysis, and we have some metrics like parameter footprint, MAC utilization, and reuse, we see two main groups, broader groups of layers, layers that are compute-centric and layers that are data-centric or memory-centric. And we call them subdivide them into 5 different layers from 1 to 5. And then we take that information and we design what we call Mensa G, which is a machine learning accelerator for those Google models at Google. And we designed 3 accelerators. They are called Pascal, Pavlov, and Jacquard. So briefly, the description of each one of them. So the Pascal accelerator is targeting the compute-centric layers that I showed previously. Mostly they are CNNs or RCNNs. And it has a 32 by 32 processing element array size, 256 activation buffer, which is an 8 times reduction compared to the baseline HTPU, and 128 parameter buffer, which is a 32 times reduction compared to the HTPU. And we keep this accelerator in the CPU die, or in the host side, not inside memory, because those applications don't necessarily have a lot of requirements of the bandwidth provide for any data processing. The second accelerator is called Pavlov, which caters for mostly data-centric LSTM layers. Since those layers does not have a lot of MAC intensity, though they don't do a lot of multiply accumulation operations, we design a much smaller processing element array size of 8 by 8 size, and we have a small activation buffer of 128 kilobytes, and we stream parameters directly from DRAM, because the parameters for LSTMs are really the size of the parameter is really large. So and there is no much reuse. So there is does not make much sense buffering them, because the buffer would need to be large, and in the end you're not going to reuse the parameters at all. So you stream them directly from DRAM. And to support that streaming, you need to place this accelerator nearby inside the DRAM chip itself. Otherwise, you cannot sustain the required memory throughput. And finally, we have Jacquard. Jacquard are for non-LSTM data-centric layers. We have a little bit larger processing element array for Jacquard, is 16 by 16, because these applications do have some MAC intensity. We have 128 activation kilobytes activation buffer and 128 kilobytes parameter buffer. And again, since the families of layers that Jacquard caters to are data-centric, we place it inside the 3D stack memory, the logic layer of a 3D stack memory in your design. So overall, if you combine the area of all of those 3 accelerators, it is still smaller than the baseline Google HTPU accelerator. So for more details about each accelerator and the data flow that we cater for each one of them, I invite you to check our paper. So we evaluate the energy and throughput utilization and area of Mensa G compared to the baseline HTPU. So I'm going to briefly talk about the results here. So here I have energy, and we have different layers in the x-axis and 3 baselines: the baseline HTPU, the baseline HTPU with a high bandwidth memory, and the Mensa G solution. And the energies are broken down into components of the subsystem. So overall, we see that Mensa G highly reduces the energy caused by parameter traffic, and also the energy caused by the network on chip, because we specialize the data flow and also you make use of processing memory. And also we can reduce dynamic energy overall compared to the baseline systems, because we avoid over provisioning for the size of the accelerator itself. We don't have such a large accelerator, monolithic accelerator anymore. So overall, when you consider all of the layers and networks and models that we have, Mensa G improves energy efficiency by 3 times compared to the baseline system. Briefly, also have the throughput analysis of those 3 systems for different layers, and we see that Mensa G also improves throughput by 3.1 times compared to the baseline system. So in conclusion, so the problem that we are having here is that we have many different network models and we have a single accelerator, right? And when you characterize this single accelerator for those different neural network models, we see that it suffers from low utilization, leading to subpar throughput, energy efficiency problems, and also memory problems. And the insight that we gain from our analysis is that the whole problem is that we have a monolithic design for the Google HTPU, even though we have a heterogeneous set of neural network models and layers. Based on that, we propose the Mensa framework, which consists of a heterogeneous set of smaller accelerators that cater for different properties, and also a runtime scheduler, a software scheduler that maps the layers to the particular accelerator. And then we evaluate it, and we see that it improves performance and energy, and also area and cost. So this was Mensa. We repeat the similar procedure for another application, which is database hybrid processing and transaction analytical databases. So the whole problem here is that you want to do real-time data analysis. So let's say that you have a self-driving car, you're having a bunch of cameras, you need to collect the data and make a decision during the execution in the quick time, right? So you're collecting translational data, and then you need to do analytical on top of the data with a deadline or in real time. So this is quite a problem, because if you don't do that analysis quick enough, the importance of the data is going to diminish. Like you already hit a pedestrian, and then like, what can you do now? To support this type of system, prior works have proposed hybrid transactional or analytical processing systems, or HTAP, which, sorry about that, that pretty much integrates in a single database management systems, transactional and analyticals. So in the end, we can support real-time data analysis. The ideal HTAP system should provide at least 3 key properties. It should provide workload-specific optimization. So transactional analytical should run as if they are running independent systems. It should provide data freshness and consistent guarantees, so that the analytical processing engine should see the most up-to-date version of the data and the consistent view of the whole system. And it also should perform, no, I mess up. Performance isolation is the same first thing that I said, and workload-specific optimization. So transactional and analytical benefits from different data layouts, for example, and then you should provide the different data layouts as required for the particular either transactional or analytical that is going to execute. However, achieving all of those 3 properties at the same time in a baseline system is really challenging. We are running out of time, but I'm going to briefly talk about the study that we can do. So we study, there are two main types of HTAP systems, what we call single instance and multiple instance systems. So single instance, both transactional and analytical run in the same replica, while in multiple instance, we have 1 replica for transactional and many replicas for analytics. And we extensively evaluate those 2 systems, and we see that they suffer for 2 main problems. The first one is that the data freshness and consistency problem or mechanisms that current systems employ are quite costly and leads to a drastic reduction in both transactional and analytical throughput when both of them are executing at the same time. And also the system fails to provide efficient performance isolation because of high memory contention when you are both executing at the same time. We have in the paper a detailed characterization, all of them, but again, due to time, I'm going to skip this part over here. I reference you to our paper. So let me move this quicker. Okay, so let's get to the problem and goals of this work. So the problem is that state-of-the-art H-step system cannot achieve all of the three desired H-step properties that you have in a system, due to the cost of maintaining data freshness and consistency, and due to contention in the shared resources of the system. So our goal is to provide a system, again doing hardware software co-design and leverage processing memory in a way that we can address this system. And based on that, we propose Polynesia. So the key idea of Polynesia is to partition the computing resources, so both memory and computation elements, into islands. And those islands are isolated for transactional or analytical. So we have, by isolating transactional data or transactional computation using transactional islands to analytical computation using analytical islands, we can apply workload-specific optimizations to each island. We also can avoid the main memory contention, and we can design efficient data freshness and data consistency mechanisms while mitigating the high cost of data movement. And all of that is further possible by leverage processing memory solutions. So here I have a quick figure of our system. So first we have the transactional islands that uses a regular CPU system to execute transactional threads, and we have analytical island, which is placed inside the logic layer of a 3D stack memory. So the analytical island constitutes of analytical cores. So those are simple processing memory cores, and specialized hardware units to maintain both a high updates between transactional and analytical threads. So there are two mechanisms for that. One that gathers transactions data and ship them to analytical replica, and also the mechanism that applied those updates to the analytical replica itself, and a mechanism to maintain consistency between transactional and analytical engines. So I would go into details about the update propagation, but I think I'm already over time. So sorry for that again. All of that is in our work. I want to go to the evaluation. Yeah. Okay. So we extensively evaluate this system using prior H-step systems and against using the Gen 5 simulator, and our implementation again is available in our GitHub, so feel free to use it. And we compare with 6 different baselines using different consistency and data consistency and data freshness mechanisms in the baseline host CPU and also ideal system. So this is some end-to-end analysis that we have in your system. So in the x-axis, we have the number of transactions, and the y-axis, we have the normalized throughputs. And basically, we see that by co-designing hardware and software to avoid the cost of data of consistency and freshness in your H-step system, we can come within 8.4% of the ideal system that consists maintaining consistency and freshness has zero cost. Also, even if you have a system that has high bandwidth, main memory bandwidth, this is not enough. We improve system performance by 63.8% by designing custom logic, so we can efficiently do the data freshness and data consistency in your H-step system. So also again, we evaluate energy, and we see that we improve energy compared to all of the baselines because we eliminate the costly DRAM access when you are doing computation. So in conclusion, the problem that you are trying to solve over here in this talk is that we have these H-step systems, hybrid transaction analytical systems that need to do computation, analytical computation over some transactional data at real time. However, that suffers, traditional systems suffer from data freshness problems, memory contention problems, and lack of performance isolation. To solve this problem, we divide the H-step system into processing islands, which enable us to do workload-specific optimizations and to provide performance isolations to both transaction and analyticals. The key mechanism that we develop is called Polynesia, which is a processing memory-based system that implement custom hardware and algorithms for data freshness and consistency, and avoids the cost of data movement across transaction and analytical threads. We extensively evaluate Polynesia, and we see that it provides a high transaction analytical throughput and reduces energy overall. So thank you so much. Sorry for rushing, but I guess with the time limitation.
Thank you, Geraldo.
Thank you.
Are there any questions for Geraldo? Okay, I have a question for you. So these applications that you have presented here, how would you expect them to perform on a general purpose architecture like AppMem that you're familiar with as well?
Yeah, so for the first one, Mensa, so Google neural networks are not quantized, so they use float point operations, and one of the main drawbacks of the UpMem system that it does not provide hardware support for float point. So float point computation is emulated, and the performance drops because of that. So the first one I would not expect to execute so well on the UpMem system. The second one, the H-step, I believe that it could highly benefit for the UpMem system, because the pin cores that we use are quite similar to the pin cores in the UpMem system itself. And the applying transactions over here, or the analytical that we are running over here, are quite simple also. So it does not require, like, for example, float point computations or multiplications, which are the main drawback of the UpMem system. So I guess, yeah, I guess database overall is a really good use case for the UpMem based system.
Thank you, Geraldo.
Thanks, Juan.
Okay.